Good morning. Today we're going to start Chapter 3 entitled Systems of Equations, and in particular 3.2. In this lecture we're going to talk about solving 2x2 systems algebraically. By 2x2 systems I mean solving two equations with two unknowns. Let me give you an example here. Let's say we are tasked with solving the following system of equations. The first equation is x plus 2y equals 4, and the second one is 2x minus y equals 3. Alright, what I'm really asking us to do is solve this system simultaneously. Some books call this technique we're talking about today simultaneous solutions. Basically, we know that if we were to graph this equation in the xy plane, we would get a line. Let's see if we can graph it. I'll make a table of values and say when x plus 2y equals 4, I can get the following solutions. When x is 0, y is 2. When x is 4, y is 0. And when x is minus 2, y is 3. All three of these points solve this first equation, and of course we can go on forever. There's infinitely many points on a line, so infinitely many pairwise solutions for any linear equation. If I look at this second equation, 2x minus y equals 3. Let me make a table of values for that equation and propose to use some solutions. Now let's say if y is 0, I get x equals 3 halves. Well, the x-intercept is then a fraction. Well, sometimes we have to deal with fractions, right? If x is 0, y is minus 3, we can see from this equation. And when x is minus 1, when x is minus 1, y is negative 5. Again, when substituting any of those three values into that second equation, I get a true statement. Alright, so what I'm going to do is graph these two lines. I'll do the best I can on the tablet here. There's my y-axis, my x-axis, not too bad. Alright, let me graph this first line equation first using those points in the yellow table. If x is 0, y is 2, puts me there. If x is 4, puts me there. And I'll just use 2 points to save time. How about in this? Well, let me go ahead and connect those two dots then. And I get the graph of the line x plus 2y equals 4. Let me fix on this pink table now. If x is 0, y is minus 3. Puts me there. And if x is minus 1, y is minus 5. Puts me there. Alright, so I can graph this line. Again, doing the best I can freehand, doesn't look too bad. And I'm going to label this second line 2x minus y equals 3. Alright, so all these points in this pink table lie on this pink line. And what I can see is, well, each line, each equation has infinitely many solutions, and I'm going to try to solve the system simultaneously. And that means to find a point that solves both equations. And of course, that's going to be the point of intersection of those two lines. And roughly looking at the graph, I think I see a point of intersection at x equals 2, y equals 1. I think you'll agree. All right, so I claim the solution to the system is the point x equals 2, y equals 1. Alright, we can check this very easily in our two equations. Remember, this point has to solve both equations. So let me write them both down here. And I'll substitute. When x is 2, y is 1. And we see indeed that that point does solve the first equation in the system. And if I substitute x equals 2, y equals 1, indeed I get a check in that second equation also. So indeed we do get a graphical solution that checks out in both given equations. Alright, graphing solutions is sometimes unreliable. Let me put this down. Perhaps unreliable, especially when your solutions fall off whole number coordinates. Alright, so what we're going to do, instead of putting forth a graphical solution method, we're going to solve systems of equations algebraically from here on in this chapter. Alright, so we're going to solve systems not using graphs, but using algebra. And there's two methods we're going to talk about here. There's the substitution method and what our book calls the elimination method, sometimes called the addition method, depending on the book that you read. And I want to talk about the substitution method first. Let's take that same equation system we were given in the beginning of the class. X plus 2y equals 4 and 2x minus y equals 3. Remember, we had a graphical solution of 2, 1. Let's see if we can arrive at that same solution algebraically. Alright, in the substitution method, basically what you do is solve for one variable and then substitute that expression in for the other variable in the other equation. Let me show you what I mean here. If I look at this first equation, I can solve for x with one very simple step: subtract 2y from both sides. Can I not? And then what I propose to do is substitute this expression for x in the other equation. That will leave me with one equation with one variable, which I should be able to solve very easily. So I get the resulting equation 2 times 4 minus 2y minus y equals 3 with that substitution. 8 then minus 4y minus y equals 3. And 8 minus 5y then equals 3. Minus 5y then equals minus 5. And of course, from this equation we get the very simple statement y equals 1. Alright, so I know in my solution for this system that y has to be 1. What I can do now is substitute this value of y in for, well, into either equation, and I get x. I'm going to use the top equation then. X plus 2 times 1 equals 4. So x plus 2 equals 4, and then x equals 2. So I know when x is 2, y is 1, and that solves the system algebraically. So my solution is the point 2, 1, which agrees with the solution we got graphically. Write that down. Agrees with the graphical solution. Okay? Alright, that's our substitution method. In a simple example, let's do a substitution method solution with a bit harder example. Solve the system. And don't panic. Yes, this equation has fractional values involved in fractional coefficients, and even worse, we've got decimal coefficients in the second equation. But with some simple surgery, we'll be able to get this into something we can handle easily. Alright, if I claim if I take the top equation and multiply through by the least common multiple of all those denominators, the fractions will disappear. So I'm going to multiply the top equation by 9. And I will get the result 2x minus 2y equals 2/3 times 9 is of course 6. Now the bottom equation, I will multiply bottom equation by of course 10. All these decimal values are in tenths, so if I multiply by 10, both sides, all terms, all these decimals will disappear. And I get the resulting equation, x equals 2 minus y. I claim this system is equivalent to the original system we started with because we did algebra things to both sides of the equations. Alright, so this resulting system begs for a substitution type solution. I can see one of the variables is already solved for, x equals 2 minus y. I can substitute 2 minus y for x in the top equation and get a resulting one equation with one unknown. So 2 times 2 minus y minus 2y equals then 6. Multiplying this out, I get 4 minus 2y minus 2y equals 6. I'll go up here. So 4 minus 4y equals 6. Minus 4y then equals positive 2, subtracting 4 from both sides. And y equals, let's see, 2 over minus 4, which of course reduces to negative 1/2. So I know that in this system, in the solution to this system, y must be negative 1/2. And of course I'll do as before. Once I've got a solution for one variable, I can just substitute into either equation here and solve for the unknown x value. Alright, so I'll pick the top equation. 2x minus 2 times minus 1/2 equals 6. Again, substituting y equals minus 1/2 for y in the first equation. So 2x minus 2 times minus 1/2 is of course positive 1. Go up here. So 2x of course equals 5, and x is then 5/2. And we know now that in this original system right here, the solution is x equals 5/2, y equals minus 1/2. So let me write that down. Solution, x equals 5/2 when y equals minus 1/2. This is the xy coordinate that solves both of those linear equations in the system simultaneously. Okay? Alright. Alright, we notice we probably would have had a hard time finding this solution graphically because of these fractional coordinates. So certainly solving things like this, solving systems algebraically, is much preferred to the graphical method. Alright, so we've done two examples of the substitution method. Now let's talk about the elimination method. And which method you pick is part of the game, I suppose. Let's look at a system here. I'm going to ask us to solve 5x plus 3y equals 2. That's a line equation. And also 2x minus 3y equals minus 16. I want to solve this system, these two equations, simultaneously, and not with the substitution method, with what we call the elimination method. Alright, what happens here? Well, I think we can see what's happening. We'll see that the y terms in both these equations cancel each other out. So if I add two equations, I will get another equation, and in this case, if I add these two equations, the y terms are going to cancel out or eliminate from the resulting equation. So if I add these two equations term by term, I get 7x plus 0, really, equals minus 14. X then equals negative 2. Alright, so I know to solve these two equations, I know x must be a minus 2, and I can pick either equation to substitute that x value into. I'll pick the second one to solve for y now. 2 times minus 2 minus 3y equals minus 16. So I'll get minus 4 minus 3y equals minus 16. Minus 3y then equals minus 12. And of course, the result for y, dividing by minus 3, y equals positive 4. So I know in this system, in solving both equations simultaneously, when x is minus 2, y is positive 4. So here's my solution, and I think you'll see our textbook does give these answers in ordered pair form. X is minus 2, y is 4. Solves these two equations by the elimination method. Alright. Let's try another one with the elimination method, one a little harder. That one was kind of rigged to cancel right from the get-go. 9a plus 5b equals 16. So here we're dealing with a's and b's instead of x's and y's. That's okay. And 3a minus 4b equals minus 6. This is a b here. 3a minus 4b equals minus 6. Solve the following system, and I'll specify by elimination. Alright, well, not quite so simple here. 9 is not a multiple of 3, and 5 is not a multiple of 4. So what shall we do here? What I'm going to do is what I'm going to do for here is number these equations. Top equation is number 1, bottom equation is number 2. What I'm going to do is leave equation 1 alone, because I see if I multiply the bottom equation through by minus 3, I will get an elimination of the a variable. Watch what happens. I'm going to take the bottom equation and multiply it by negative 3. I'll indicate that with a minus 3 times number 2. I'll get a minus 9a, see what happens? And then minus 4b times minus 3 is plus 12b. equals minus 3 times minus 6 is positive 18. Alright, so by doing a little surgery on the bottom equation, I can rig things so I'll get a cancellation of the a variable. Alright, so 9a minus 9a is 0, 5b plus 12b is 17b, and 18 plus 16 is of course 34. And 34 is 2 times 17, so we get a solution for b of b equals 2. I can substitute now b equals 2 into any of the equations I see above. I'm going to pick number 2, the original number 2 equation. I'll say 3 times a minus 4 then times 2 equals minus 6. So 3a minus 8 equals minus 6. 3a then equals, well, if I add 8 to both sides, 2. And a equals 2/3. Again, a fractional coordinate. That's okay. So I claim the solution to my original system of equations is a equals 2/3 and b equals 2. So I'll write it just like this, my solution, and we usually put the variables in alphabetical order when we're in ordered pair notation. X comes before y, a comes before b, etc. So there's my solution via the elimination method. A equals 2/3, b equals 2. Alright, up the ladder we go. Let's try another one. Solve. Again, I'll specify by the elimination method. We've done 2 already. Top equation. 4x equals 3 times 2 plus y. And the bottom equation, 3 times x minus 10 equals minus 2y. Now this one very much does not look like the ones we've done thus far. That's okay. What I'm going to do is convert both equations to what we call standard form. And by that I mean a multiple of x plus a multiple of y equals some constant. And I can do that pretty easily doing algebra things to the equations. Let me show you what I mean. If I look at the top equation, well, what I want to do is multiply things out to free up variables from their parentheses. In the top equation, I'll get 4x equals 6 plus 3y. That's a plus there. Top equation turns into 4x equals 6 plus 3y. And in the bottom equation, I get 3x minus 30 equals minus 2y. So I really haven't changed anything except the form in which these variables and numbers appear. One more step. The top equation, I'm going to subtract 3y from both sides. Resulting in standard form equation on top. And on the bottom, well, I can add 2y to both sides and at the same time add 30 to both sides, resulting in 3x plus 2y equals 30. Alright, so I've converted with some simple steps both of my equations into standard form. And I notice that 4 is not a multiple of 3. And similarly, 3 is not a multiple of 2. Alright, well, I'm going to have to do what I call double surgery in this situation in order to get an elimination of one variable or the other. Alright, I think I see what I'm going to do. I'm going to go for a elimination of the y variables here. Notice the signs are opposite. So if I can get the y variables to have coefficients that are equal in magnitude but opposite in sign, I'm going to be able to eliminate the y variable. I'm going to call this equation 1. I'm going to call this equation 2. I'm going to take the first equation and multiply it through by a positive 2. Watch what happens. 8x minus 6y equals 12. Again, here my goal is to eliminate the y variables, so then I'm going to take my second equation and multiply it by a positive 3. And I'll get a 9x plus 6y equals 90. Now I haven't changed anything regarding the solution. I've done algebra things, balanced basically both sides of the equations, getting things in a convenient form, and here that means eliminating one of the variables, namely the y variable. Alright, so with that double surgery, I can easily eliminate the y variable now. I'll get 17x equals 102. And I believe 102 is a multiple of 17. Yes, it is. And x equals 6. Alright, so in this solution to the system, I know x has to be 6. And I can plug x equals 6 into any of these above equations to solve for y. I think I'm going to pick this equation. Alright, x has to be 6. So I can plug in x equals 6 into that second equation and get the resulting statement. 3 times 6 plus 2 times y equals 30. That gives me 18 plus 2y equals 30. 2y equals, of course, 12. And y then also equals 6. Alright, so with some conversion and some clever double surgery, I can arrive at a solution to the given system when x is 6, y is 6. So there is my point of simultaneous solution for both of those equations. Alright, one more, we'll call it a day for this section. And this one's a little nastier. This one I think is the last one in your homework assignment. 12x minus 5y minus 21 equals 0. And 3/4 x plus 2/3 y equals minus 13/8. Yeah, don't panic. With a little housekeeping, we can convert both of these into standard form and perhaps even equivalently get rid of the fractions and solve these in not too difficult fashion. It's going to require a little work. The top equation, I'm going to just add 21 to both sides. That will give me the resulting 12x minus 5y equals 21. Looks better already. The bottom equation has got some nasty fractions in it, and we don't like fractions, so I'm not going to deal with the fractions. I'm going to multiply the bottom equation by the least common multiple of all these denominators, which of course is 24, right? 24 is the least quantity that is a multiple of 3 and 4 and 8. Alright, you've got to apply your distributive law correctly. 24 times 3/4 x, well, 4 goes into 24 6 times, and 6 times 3x is 18x. And the fraction goes away. Alright, that takes care of 24 times 3/4 x. What about 24 times 2/3 y? Well, cross-canceling, 3 goes into 24 8 times, and 8 times 2y is plus 16y. Equals. Now on the right, 8 goes into 24 3 times, and 3 times minus 13 is minus 39. Alright, so with a little careful housekeeping, I have got things, both equations in standard form with no fractions to deal with. Alright, what I'm going to do, well, I'm going to take the, let me rewrite this now. I want to get this lined up real nice. I'm going to get my resulting 2 by 2 system. That means 2 equations with 2 unknowns. And now 18 is not a multiple of 12 and 16 is not a multiple of 5. So it looks like I'm going to have to do some double surgery here. I'm going to take this first equation, this top equation, and multiply by positive 3. Why am I doing that? Well, I think I can say 3 times 12, x is 36x, and I'm going to look to eliminate the x variable. Right? 36 is also a multiple of 18. Alright, so I'm going to multiply the top equation through by 3, and multiply the bottom equation through by a negative 2. I think we'll be able to eliminate the x variable quite nicely then. Watch what happens here. I'll get a 36x minus 15y equals 63 on the top equation, an equivalent equation, right? And on the bottom, multiply through by negative 2, I'll get a negative 36x. See what I did that? Minus 32y, be careful of the signs, equals positive 78. Alright, now it's a breeze. I can eliminate my x variables. I'll get minus 47y equals, let's see, 141. And y then equals negative 3, dividing both sides by negative 47. Alright, so my point of solution contains a y value of minus 3, and I can go to any other equation that appears that has both variables in it. I think I'm going to pick this one to solve for x once I know that y equals minus 3. 12x minus 5 times minus 3 equals 21. So 12x plus 15 equals 21. 12x then equals 6, subtracting 15 from both sides, and I get x equals 6/12 or 1/2. 6 over 12 reduces to 1 over 2. So when y equals minus 3, x equals 1/2, and that is my point of solution for the given system above. Alright, we'll call it a day, and that's section 3.2, solving systems algebraically, solving 2 by 2 systems algebraically.